When we start talking about grounding concepts, the way they were explaining it here is we're going to use a solid footing or foundation to build a building, and many times what we use to make our connection to the earth is provided for us already by other trades. They may have concrete encased electrodes that are installed. They may have metal in-ground support structures. So this is trying to relate that to a solid foundation of the building. We want a solid foundation for our grounding system. So it's the foundations of it, so it functions properly. And we mentioned earlier that the reason for grounding systems is to stabilize those systems under normal and abnormal conditions. And here it says sometimes it's referred to as earthing. Well, some other standards actually call it earthing. And the NEC is stuck with calling it ground, but simply defining ground as being the earth. When we solid ground our systems, and that's a very common method of doing it, we're connected to ground through our grounding electrode conductors, ultimately getting to our grounding electrodes or grounding electrode system, and we haven't added any intentional impedance. So all my grounding electrodes are going to have to be bonded together. We're going to see those rules when we get to 250.50, and that's our foundation of our electrical system. Many people have heard the phrase, electricity takes the path of least resistance. That's kind of been a long time phrase, but it's actually not true. Electricity doesn't take the path of least resistance. Electricity takes all paths that are available. Most of the current is going to be on the path of least resistance. But if there's multiple paths, we'll have current on all those paths. And the current's going to divide in opposite proportion to the resistance or the impedance, typically for our AC systems. When we're designing our systems, one of the goals in the NEC, and it's kind of an unwritten goal, is to avoid parallel paths for current for normal current, unless we're doing a parallel conductor installation. That's something different. But we want current to stay on the intended paths that we provide for it, essentially on our insulated conductors. We don't want current under normal conditions on our metal raceways or metal enclosures or any other conductive objects. And the way to accomplish that is by only grounding our systems at a single point. And that's the concept that's all highlighted here. Obviously, it's saying that the lower impedance path is going to carry more current than the higher impedance path. And then we've got rules that apply for how we go about installing those. This is just a very basic installation. Here's a series path. Now we have parallel paths. So the current's going to divide based on all of those paths. And same thing here. So we've got a source of a supply dry system. And here's where the confusion is, because the source isn't here. The source is the output. That's my source of my supply dry system. So if I have, we're not showing the ungrounded conductors going out to supply something. We have a ground fault condition coming back. And now if we have multiple paths, it's going to have current on all these multiple paths going back to our source. So the wording that's used in a number of different training programs is current always tries to return to the source. And I kind of think about it as, well, I start with a voltage source, and there's a voltage between those two. So the only time I'm going to have current is if current goes out and it comes back to this point. Current doesn't go out to some point and just disappear into the earth. So I need a complete circuit. And that applies to both my normal circuit conditions and also under ground fault conditions.